Module 18, Lecture A, Boosted Trees. By the end of this lecture, you will be able to fit gradient boosting classifiers and regressors for supervised tasks, tune learning rate, estimator count, subsampling, and early stopping, and use histogram gradient boosting features such as native categories, missingness, and monotonic constraints. Gradient boosting basics. Gradient boosting classification. Gradient boosting classification creates a strong predictor by adding simple decision trees one after another. Each new tree focuses on patterns the current model is still uncertain about, gradually improving the overall predictions. By combining all the trees, the model can capture complex nonlinear relationships and interactions that a single tree may miss. A gradient boosting classifier begins with a simple baseline prediction, such as the overall class distribution, then adds many shallow trees to improve it step by step. Each tree makes a small correction, capturing limited patterns like churn risk from account history, support calls, or usage changes. For classification, the model estimates probabilities or support for each class, and the final label is chosen using those estimates and the selected decision rule. Gradient boosting classification uses decision trees to make accurate predictions on structured data with numerical or categorical features. It can find complex patterns, such as signs of fraud or students needing support, but it must be controlled to avoid overfitting from too many or overly complex trees. Model quality should be checked on validation data, while also considering the real-world cost of mistakes, like approving risky loans or wrongly flagging valid transactions. Python code, gradient boosting classification. This example uses a gradient boosting classifier where shallow trees improve predictions in stages. Its test accuracy indicates how well the model generalizes to unseen flower data. We import Scikit-Learn tools for a simple classification workflow: the iris dataset loader, a gradient boosting classifier, an accuracy measure, and a train test split utility. Together, these let us load the data, divide it into training and testing sets, train a tree-based ensemble model, and evaluate its performance on unseen data. We load the iris dataset with Scikit-Learn's built-in tool as a simple example for multi-class classification. It includes flower measurements as features and species labels as targets, making it easy to prepare data for training and evaluating a model. Before training, the code verifies that the feature data and target labels have the same number of entries. This ensures every feature row has a matching label. If they do not match, it raises an error to prevent problems during model training. We split the dataset into training and testing sets so the model can be evaluated on data it has not seen before. Using Scikit-Learn's train test split function, 30% of the data is reserved for testing and 70% for training. The split is stratified to preserve the original class balance, and a fixed random state makes the results reproducible. We configure a gradient boosting classifier made of 60 shallow decision trees. A learning rate of 0.08 lets each tree make a small contribution, supporting gradual improvement, while limiting tree depth to 2 keeps the model focused on simple patterns. A random state of 42 makes the results reproducible. The model is trained by fitting the gradient boosting classifier to the training features and target labels. During this process, it adjusts its parameters to reduce prediction errors and learn useful patterns in the data. The trained gradient boosting classifier is used to predict the class of each test sample from its features. It also estimates the probability of each possible class, showing how confident the model is in its predictions. The model is evaluated by comparing its predicted classes with the true test labels to calculate accuracy. For the first test example, the predicted class index is used to identify the corresponding iris species. The highest predicted probability for that example then shows how confident the model is in its prediction. The output reports the scikit-learn version for reproducibility, then shows the model's test accuracy to summarize performance on unseen data. It also gives the predicted class and confidence for the first test sample, providing a quick view of how certain the model is for that case. This script trains a gradient boosting classifier on the iris dataset, using a stratified train test split to preserve class balance. The model uses small decision trees and a modest learning rate to improve predictions step by step. After training, it predicts test labels and probabilities, reports the test accuracy, and shows the first test sample's predicted class with its confidence, along with the scikit-learn version used. Gradient boosting regression. Gradient boosting regression predicts continuous values by combining many simple decision trees built in sequence. Each new tree focuses on correcting the errors left by earlier trees, so the model gradually improves where its predictions are weakest. Over time, this targeted correction helps produce more accurate results. Gradient boosting regression builds predictions by combining many small trees, each one making a small correction to the errors left by the previous trees. It often reduces squared error, which helps the model focus on larger mistakes. In a sales example, early trees may capture broad patterns like seasonality, while later trees refine the prediction using details such as holidays or promotions. This step-by-step process lets the model learn complex relationships. Gradient boosting regressors work by combining many simple trees rather than making each tree highly complex. This helps the ensemble capture patterns in tabular data with complex interactions, such as used car pricing. If the model becomes too flexible, it can learn noise instead of useful structure. So the goal is to balance complexity with generalization to perform well on new data. Python code. Gradient boosting regression. Fit a gradient boosting model for continuous prediction by building trees in sequence, where each new tree reduces the remaining regression error. Then, evaluate the model by comparing its predictions with held-out target values. This setup imports the main tools needed for a regression workflow: numerical computing with NumPy, visualization with Matplotlib, and machine learning with Scikit-Learn. It loads the diabetes dataset, prepares a gradient boosting regression model, and uses mean absolute error to measure prediction accuracy. The data is split into training and testing sets, so the model can be trained on one portion and evaluated on another. We begin by using Scikit-Learn's built-in diabetes dataset, which is designed for regression. It includes input features and target values, giving us a ready-made real-world dataset for predicting outcomes. This makes it a convenient choice for demonstrating regression without extra data collection or preprocessing. Before training, confirm that the feature data has the same number of rows as the target values. This ensures every feature set has a matching target. If the counts differ, raise an error to prevent mismatched data from causing training problems. We split the dataset into training and testing sets using Scikit-Learn's train test split function. 25% of the data is held back for testing, and a fixed random state makes the split reproducible. This lets us train the model on one portion of the data and evaluate it on unseen data, helping check performance and reduce overfitting. A gradient boosting regressor is created with 80 sequential trees, a learning rate of 0.05. and shallow trees limited to a depth of 2. A fixed random state ensures reproducible results. The model is then trained on the feature and target data, building trees one after another to reduce prediction errors. The trained gradient boosting model is used to predict target values for the unseen test data. Its performance is then evaluated with mean absolute error, which shows the average size of the prediction errors compared with the actual values. The code first reports the Scikit-Learn version to support reproducibility. It then evaluates the model by printing the mean absolute error on the test set, which shows the average size of the prediction errors. Finally, it compares the first predicted value with its actual target value to give a quick check of how close the model is. This visualization compares actual disease progression scores with the scores predicted by a gradient boosting regression model. A scatter plot shows the test patients with slight transparency to make overlapping points easier to see. A perfect prediction line is added as a reference, so points closer to the line indicate more accurate predictions. The plot includes clear axis labels, a title, and a legend before being displayed. This script trains a gradient boosting regression model on the diabetes dataset, using a train test split to evaluate performance. The model is fitted with a modest learning rate and shallow trees, then used to predict outcomes for the test data. Its accuracy is measured with mean absolute error, and one prediction is compared with its actual value. A scatter plot of predicted versus actual values, with a perfect prediction reference line, helps show how well the model performs. Boosting losses. Boosting losses tell a gradient boosting model what counts as an error and how strongly each error should shape the next tree. As trees are added one after another, the model focuses on the mistakes that remain. The loss function depends on the task. Regression targets prediction errors, while classification also rewards confident, correct class probabilities. In this way, the loss function guides the model toward more accurate and well-calibrated predictions. In regression, the loss function determines how the model treats errors and outliers. Squared error loss strongly penalizes large mistakes, which can be useful when big errors are costly, but it may also make the model too sensitive to rare extreme cases. Other losses reduce the influence of unusual values and can make the model more robust. The best choice should match the real cost of errors while still capturing typical patterns. In classification, boosting losses help models produce reliable class probabilities, not just labels. This matters when decisions depend on confidence and when error costs require flexible thresholds. During training, boosting gives more attention to misclassified or uncertain cases, improving performance on difficult examples. The key is to control this focus so the model learns useful patterns without fitting noise. Python code, boosting losses. This example compares two loss choices for boosting regression and shows how they affect learning from outliers. The printed scores highlight which loss behaves more robustly when outliers are present. We import NumPy for numerical work and array handling, along with Scikit-Learn for machine learning tools. From Scikit-Learn, we use a gradient boosting regressor for regression, mean absolute error to measure prediction accuracy, and a train test splitting utility to evaluate the model on unseen data. We create a small regression dataset with a clear pattern by generating evenly spaced values from 0 to 10. A fixed random seed makes the results reproducible, and normally distributed noise is added to simulate real-world variation in the data. The target values are created by doubling each input value and adding noise, producing a mostly linear pattern with small variation. Then, every 20th position is selected, and the target value is increased by 12, creating large outliers. These outliers make the data more challenging because squared error loss is especially sensitive to extreme values. The input values are reshaped into a two-dimensional matrix because Scikit-Learn expects features in that format, even with only one feature. Using the reshape method lets each value become its own row while keeping the data size consistent. The target values are then assigned separately, so they stay aligned with the features for model training. Before training the model, the code verifies that the feature data and target data have the same number of rows. This ensures each set of features has a matching target value. If the counts differ, it stops with an error to prevent training problems caused by mismatched data. The dataset is divided into training and testing sets using Scikit-Learn's train-test-split function, so both models are evaluated on the same test data. 30% of the data is reserved for testing, and a fixed random state of 42 makes the split reproducible. A gradient boosting regressor is created using squared error loss, which makes larger prediction errors more influential during training. The model uses 80 trees with a learning rate of 0.08 and a fixed random state for reproducible results. It is then trained on the data to learn the relationship between the input features and target values. We build a gradient boosting regression model using absolute error loss, which makes it more robust to outliers in the target values. The model uses 80 estimators, a learning rate of 0.08, and a fixed random state for reproducible results. It is then trained on the data to learn the relationship between the features and the target. We evaluate both models using mean absolute error on the test set. First, we compare the squared loss model's predictions with the true target values. Then repeat the same process for the absolute loss model. Using the same metric for both makes their performance directly comparable and helps show how each loss function responds to outliers. We first note the Scikit-Learn version to support reproducibility, then compare two models using mean absolute error. One model uses squared error loss, and the other uses absolute error loss. The lower mean absolute error indicates better typical predictions on the noisy test set, helping show which loss function gives more robust performance. This script compares squared error and absolute error loss in a boosting regression model using synthetic linear data with added outliers. Both models are trained and tested on the same split, then evaluated with mean absolute error. Squared error is more affected by extreme values, while absolute error is usually more robust and often performs better when outliers are present. The main lesson is that the loss function should match the data and the need for robustness. Boosting control, learning rate trade-off. In boosted trees, the learning rate controls how strongly each new tree changes the model as it corrects earlier errors. A high learning rate can learn patterns quickly, but may overfit noise, while a low learning rate makes smaller updates that are usually more stable and generalize better when enough trees are used. In short, larger corrections are faster but riskier, and smaller corrections are slower but smoother. The learning rate and number of estimators must be tuned together because they trade off with each other. A lower learning rate makes each tree contribute less, so more trees are needed, while a higher learning rate can use fewer trees but may overreact to unusual training cases. In credit risk modeling, a slower learning rate helps ensure patterns are supported by multiple trees before strongly influencing predictions. Choosing a learning rate means balancing training speed with accuracy and generalization. Smaller rates can produce stronger models but need more trees and more time, while larger rates train faster but may overfit or generalize poorly. Validation monitoring and early stopping help decide when adding trees no longer improves performance. The goal is steady learning that captures real patterns without memorizing noise. Python code, learning rate trade-off. In gradient boosting, the learning rate controls how large each update is. Smaller learning rates usually require more trees to reach good performance. Validation curves help show this trade-off clearly. We import key tools for building and evaluating a classification model. Matplotlib is used for plotting, while Scikit-Learn provides utilities to create a synthetic classification dataset. Split it into training and validation sets, train a gradient boosting classifier, and measure performance using log loss. We create a synthetic classification dataset using Scikit-Learn's make classification function. It contains 1,200 samples with 12 features, including 6 informative features and 2 redundant ones derived from them. A fixed random state of 42 makes the data reproducible, which helps compare machine learning models under consistent conditions. We split the dataset into training and validation sets using Scikit-Learn's train test split function. 30% of the data is reserved for validation, while stratification keeps the class distribution consistent with the original dataset. A fixed random state makes the split reproducible across runs. Before modeling begins, the code checks that both the training and validation datasets contain rows. If either dataset is empty, it raises an error and stops the process. This ensures the model has data to learn from and data to validate against, avoiding later runtime problems. This line shows which version of Scikit-Learn is being used. Knowing the version helps with compatibility, reproducibility, and debugging, because behavior can differ between releases. We define 3 learning rates, 0.03, 0.1, and 0.3, to control the model's training step size. We also assign blue, green, and red to distinguish the corresponding validation loss curves in the plot. We first create a plot for the validation loss curves. This gives us a clear space to compare how different learning rates affect the performance of the gradient boosting models. We compare several learning rates by training a gradient boosting classifier for each one. Each model uses the same number of trees and a fixed random state, so the results are reproducible and directly comparable. This lets us see how the learning rate affects model performance. The gradient boosting classifier is trained on the training data, so it can learn patterns between the features and targets. After training begins, a list is prepared to record validation losses as more trees are added. This helps track how well the model performs on unseen data. The loop checks the model's predicted probabilities at each stage on the validation data and calculates the log loss against the true targets. Lower log loss means the predictions are better aligned with the actual outcomes. These losses are stored, so performance can be tracked as the number of trees changes. The process finds the lowest validation loss to identify the model's best validation performance. It then uses that loss's position in the list to determine how many trees produce the best result, adjusting for zero-based indexing. Finally, it creates a plot label showing the learning rate and the best number of trees, making the model's performance easier to compare visually. The code compares validation log loss as more trees are added to the model, from 1 to 120 trees. It plots a separate line for each learning rate, labeling each with the learning rate and the tree count that gives the best validation loss. It also prints the best validation log loss for each learning rate, making it easier to compare how learning rate affects model performance. The plot is labeled to show the learning rate trade-off in gradient boosting. The horizontal axis shows how many trees have been added, while the vertical axis shows validation log loss, where lower values mean better performance. A legend identifies the different learning rates, so the comparison is easier to understand. Finally, we use the matplotlib show function to display the completed plot. This lets us compare the validation loss curves for different learning rates in the gradient boosting models and analyze the results visually. This script shows how learning rate affects a gradient boosting classifier. It trains models with learning rates of 0.03, 0.1, and 0.3, then tracks validation log loss as more trees are added. The results illustrate the main trade-off. Smaller learning rates usually need more trees to perform well, while larger learning rates improve faster but may overfit. Stochastic boosting. Stochastic boosting adds controlled randomness by training each new tree on a random subset of the data instead of the full dataset. This helps reduce overfitting because the model is less likely to focus on unusual details or minor patterns in the training data. In tasks like customer churn prediction, it can lead to more stable and generalizable patterns across the customer base. In stochastic boosting, the subsampling rate controls how much training data each tree uses. Using less than all the data adds randomness, which can reduce variance and help the model generalize better. But if the rate is too low, each tree may have too little data to learn reliably. The goal is to balance randomness with enough information for stable, meaningful learning. Stochastic boosting should be tuned together with the learning rate and number of trees, not in isolation. Lower learning rates and subsampling usually require more trees to offset randomness and build a smoother, more generalizable model. Because validation results can fluctuate when each tree uses a different data subset, use early stopping carefully. In areas like fraud detection and demand forecasting, this controlled randomness can improve performance on new data. Python code, stochastic boosting. Full data gradient boosting uses all available training data at each step, while stochastic gradient boosting adds controlled randomness through subsampling. This randomness can act as regularization, helping reduce overfitting. Comparing validation scores shows how subsampling affects model performance. We import key Scikit-Learn tools for a regression workflow, a function to create synthetic regression data, a gradient boosting regressor to build an ensemble of decision trees, a metric to measure mean absolute error, and a utility to split the data into training and testing sets. Together, these tools let us generate data, train a model, and evaluate how well it performs on unseen examples. We create a synthetic regression dataset using Scikit-Learn's make regression function. It includes 1,200 samples and 12 features, with added noise to better reflect imperfect, real-world data. A fixed random state makes the dataset reproducible, giving us a consistent setup for testing models. The dataset is split into training and testing sets, so both models can be evaluated on the same held-out data. Using Scikit-Learn's train-test-split function, 25% of the data is reserved for testing, and a fixed random state makes the split reproducible. The split produces separate training and testing data for both the features and the target. First, we verify that the training features have 12 columns, matching the expected 12 inputs for the lesson. This simple check confirms the data is in the right format before training. If the column count is wrong, the code raises an error, so the issue can be fixed early. We create a gradient boosting regressor and train it on the data to learn patterns in the target values. The model uses 180 sequential trees, with a learning rate of 0.05 to control each tree's contribution. It uses the full training set for each tree, and a fixed random state ensures the results can be reproduced. We create a stochastic gradient boosting regression model using Scikit-Learn. It builds 180 trees with a learning rate of 0.05 and each tree trains on a random 60% of the data to reduce overfitting. A fixed random seed makes the results reproducible, and the model is then fit to the training data to learn patterns for prediction. Calculate the mean absolute error for the full model on both the training and test data. The training error shows how well the model fits the data it learned from, while the test error shows how well it performs on new data. Comparing the two helps evaluate overall model performance and generalization. We use mean absolute error to evaluate the stochastic model on both training and test data. It shows the average size of the prediction errors compared with the actual values, regardless of direction. The training score reflects how well the model fits known data, while the test score indicates how well it generalizes to unseen data. The output first checks the Scikit-Learn version to support compatibility and reproducibility. It then compares mean absolute error on the training and test data for both the full data boosting model and the stochastic boosting model. The stochastic version adds controlled randomness by training each tree on a subsample. So a subsample of 0.6 means each tree uses 60% of the rows. This script compares standard gradient boosting with stochastic gradient boosting on a noisy synthetic regression dataset. One model uses all training data for each tree, while the other uses only 60%, adding randomness through subsampling. Both are evaluated with mean absolute error on training and test data. The full data model often fits the training set better, but may overfit, while the stochastic model can act as a regularizer and produce a better balance between training and test performance. Early stopping. Early stopping helps decide when a boosted tree model has trained enough. As gradient boosting adds trees, performance may improve at first, but too many trees can make the model overfit noise in the training data. By checking performance on a validation set and stopping when improvement stalls, early stopping keeps the model accurate without making it overly specialized. Early stopping works best when validation performance is measured carefully, and the model is given enough patience before training stops. Because validation scores can fluctuate between boosting rounds, stopping after the first non-improvement can end training too soon. A patience setting waits through several rounds to see whether performance improves again, which is especially useful with noisy data, subsampling, or small learning rates. Early stopping works closely with the learning rate and the number of trees in an ensemble. Smaller learning rates often generalize better, but need more trees, so validation-based stopping helps choose when to stop. Larger learning rates may improve quickly, but can overfit, making monitoring important. In tasks like readmission prediction or fraud detection, early stopping helps select models that perform well on new data. Python code. Early stopping. Early stopping in gradient boosting means monitoring validation accuracy as each new tree is added. Once the validation score stops improving, additional trees are no longer helping and may be unnecessary. This shows where training should stop to keep the model effective without adding extra complexity. We import the main tools needed to build and evaluate a classification model. Matplotlib supports plotting, while Scikit-Learn provides functions to create a synthetic classification dataset. Split it into training and validation sets. Train a gradient boosting classifier and measure prediction accuracy. We create a controlled classification dataset with Scikit-Learn's make classification function to test model performance. It contains 1,200 samples with 12 features, including 6 informative features and 2 redundant ones. A fixed random state of 42 ensures the same dataset is generated each time. We use Scikit-Learn's train test split function to divide the data into training and validation sets, keeping the validation data unseen during model fitting. 30% of the data is reserved for validation, while stratification preserves the original class balance. A fixed random state makes the split reproducible. Before training begins, the code checks that both the training and validation datasets contain rows. If either one is empty, it raises an error to stop the process. This prevents training or validation from running without the data the model needs. We create a gradient boosting classifier with up to 120 trees, a learning rate of 0.05, and an 80% subsample to help limit overfitting. A fixed random state of 42 makes the results reproducible. The model is then trained on the training features and targets by adding trees step by step to improve prediction accuracy. To track boosting performance, we store validation accuracy after each stage. The model generates predictions after each added tree, and each set is compared with the true validation targets. These accuracy scores show how performance changes as boosting progresses. To choose the best stage in gradient boosting, we find where the validation accuracy is highest and treat that point as the model's best performance. Because the index starts at 0, we add 1 to get the corresponding number of trees, then record the best validation score. A patience value of 10 is also set to help stop training when adding more trees no longer improves performance enough. Early stopping is simulated by choosing the number of trees based on the best validation score plus a patience allowance, without going beyond the available scores. This determines where training would stop and how many trees to keep. The final validation score is then taken from the last recorded score, showing accuracy after all trees were used. The output reports key training results for the model, the Scikit-Learn version, the best validation accuracy, and the number of trees where that accuracy occurred. It also shows where early stopping would stop adding trees based on the patience setting, then compares this with the accuracy after using all 120 trees. The plot shows how validation accuracy changes as the number of boosted trees increases. It highlights the tree count with the best validation score and the early stopping point, where adding more trees no longer improves performance. A title, axis labels, and legend make the chart clear and help interpret the model's behavior during early stopping. This script shows how early stopping can be used with gradient boosting for classification. It trains a model, checks validation accuracy after each added tree, and finds the tree count where accuracy is highest. It then compares that best point with the final model after all trees are used, while also marking an early stopping point based on a patience of 10 trees. The main idea is to show when adding more trees no longer improves validation performance. HistGradientBoosting. HistGradientBoosting basics. Histogram gradient boosting makes traditional gradient boosting faster and more scalable by grouping continuous features into bins instead of testing every possible split value. The model then searches for good splits within these ranges, which greatly reduces computation while preserving predictive accuracy. This is especially useful for large datasets, where it can train more quickly while still capturing complex relationships among variables. Histogram gradient boosting is well suited to structured data, where rows are observations and columns are attributes. It uses decision trees to model nonlinear patterns and interactions, making it useful for tasks such as predicting loan defaults, product demand, or customer cancellation. By grouping values into bins, it finds tree splits efficiently, so it can work well on large datasets. Histogram gradient boosting handles messy real-world data by grouping feature values into bins, making it efficient with missing values, categorical variables, and prediction constraints. It can also respect business rules, such as keeping risk predictions consistent with higher debt. This makes it a practical framework for building interpretable models that capture complex patterns, while staying aligned with real-world requirements. Python code. HistGradientBoosting basics. This example trains a histogram gradient boosting model to show how it handles missing values and monotonic constraints. It then compares predictions from constrained and unconstrained versions of the model. We import NumPy for numerical array operations and use Scikit-Learn for machine learning tools. From Scikit-Learn, we bring in the histogram gradient boosting regressor for regression modeling, mean absolute error to measure prediction accuracy, and train test split to divide the data into training and testing sets for evaluation on unseen data. We create a small, reproducible regression dataset by using a fixed random seed and 800 samples. The income values are randomly generated between 20 and 120, giving a consistent dataset for model training and testing. A second feature, called debt ratio, is created by generating random values between 0.05 and 0.75 for each sample. To mimic incomplete real-world data, some of these values are then randomly marked as missing. Any selected entries are replaced with nan, creating a dataset with intentional missing values. Random noise is generated from a normal distribution, with mean 0 and standard deviation 8, to represent real-world variation. The risk score is then based mainly on income reduced by the debt ratio, with the noise added in. Any missing debt ratio values are replaced with 0.4 before the calculation. Overall, the model assumes higher income raises the risk score, while higher debt can lower it. Income and debt ratio are combined into one 2-column matrix, with each row representing a sample. Before training, the matrix shape is checked to confirm it has 800 rows and 2 columns. If the shape is incorrect, an error is raised to prevent using improperly structured data. We split the dataset into training and testing sets using Scikit-Learn's train test split function. 25% of the data is kept for testing, and a fixed random state ensures the split can be reproduced. This lets the model learn from one portion of the data and be evaluated on unseen data to check how well it generalizes. We create a histogram gradient boosting regressor with 80 maximum iterations, a learning rate of 0.08, and a fixed random state for reproducible results. We then train it on the prepared features and target values, so it can learn how the inputs relate to the risk score. We train a histogram gradient boosting regressor with a monotonic constraint, so predictions must rise as income increases. Income is constrained to have an increasing effect, while debt ratio is left unconstrained. The model is then fit to the training data while respecting this rule. We compare the basic and monotonic constrained models using mean absolute error, which shows the average size of prediction errors regardless of direction. By measuring this error on the test data for both models, we can see whether adding the monotonic constraint improves or reduces accuracy. We create a test grid where income varies from 30 to 110, while the debt ratio is left missing. The missing debt values are represented with not a number entries, matching the income values. These two pieces are combined into one grid to test how the model predicts risk scores when income changes but debt information is unavailable. The output first reports the Scikit-Learn version to support reproducibility, then compares the mean absolute error of the basic and constrained models. It also displays a readable income grid and the constrained model's rounded predictions across that grid. Together, these results show how the constrained model performs and how its predictions change as income increases when debt information is missing. This script shows how histogram gradient boosting can handle missing values and use monotonic constraints in regression. It creates synthetic income and debt data, with some debt values missing, then trains a basic model and a constrained model that forces predictions to rise as income increases. Both models are tested with mean absolute error, and the constrained model is examined on cases where debt is missing. The results illustrate how monotonic constraints can guide predictions in a more consistent direction when important feature values are unavailable. Native categories. Histogram-based gradient boosting can handle categorical features directly, so one-hot encoding is often unnecessary. This helps avoid expanding the feature space and prevents the model from treating unordered categories, such as regions, product types, or contract types, as if they had a numeric order. By keeping categories as distinct labels, the model preserves their meaning and uses them more appropriately. Native categorical features let models learn useful category groupings directly, reducing the need for heavy preprocessing. In boosted trees, these categorical splits can lower prediction error by grouping categories with similar patterns, while keeping the original feature meaningful. This simplifies the modeling pipeline, avoids many extra derived columns, and supports better performance and maintainability. Native categorical handling works best when the data is carefully prepared. Keep category labels consistent. Combine very rare categories when needed, and plan how to handle new categories that appear during prediction. The algorithm can group categories effectively, but good results still depend on domain knowledge and thoughtful data cleaning. Python code, native categories. This demonstrates native categorical handling in histogram boosting for price prediction. Categorical labels are treated as distinct groups rather than ordered values, allowing the model to learn from mixed feature types correctly. We import NumPy for numerical work and random number generation, and pandas for organizing and analyzing data with data frames. We also import Scikit-Learn for machine learning tools, along with its column transformer, which lets us apply different preprocessing steps to different data columns, especially when the dataset contains mixed data types. These imports prepare the tools needed to build and evaluate a price prediction model. They include a histogram gradient boosting regressor for regression with numerical and categorical features, mean absolute error to measure prediction quality, and a train test split to evaluate performance on unseen data. A pipeline helps combine processing steps with the model, while an ordinal encoder can convert categorical values into integer codes when needed. We set up a reproducible housing dataset by using a fixed random seed and choosing 240 samples. We also define 4 neighborhood types: central, suburb, riverside, and industrial. These categories will be used to model how different areas can affect housing prices. We create a dataset with both numeric and categorical predictors. The numeric features include area values drawn from a normal distribution and limited to a realistic range, along with randomly generated ages. Each sample is also assigned a random neighborhood category, giving the model a mix of feature types to learn from. A dictionary is used to assign each neighborhood category a price effect, showing how location changes the simulated price. Central has the strongest effect, followed by riverside and suburb, while industrial has the smallest impact. These values let the model adjust prices based on neighborhood type. The target price is created by combining several simulated influences. Each selected neighborhood is assigned a price effect. Random noise is added to represent real-world variation, and the final price is based on a base value adjusted by area, age, neighborhood effect, and noise. This produces a realistic regression target that reflects both structured patterns and randomness. We organize the data in a pandas data frame with each sample's area, age, and neighborhood. The neighborhood information is then converted to a categorical type, so the model treats each label as a distinct category rather than an ordered value. We split the dataset into training and testing parts, so the model can be evaluated fairly on data it has not learned from. Using Scikit-Learn's train-test-split function, we reserve 25% of the data for testing. A random state of 42 makes the split reproducible, so results stay consistent across runs. We first confirm that the neighborhood column in the training data is still treated as categorical. This check helps ensure the model can process the data correctly. If the column is not categorical, an error is raised to signal that something has gone wrong. We configure the HistGradientBoosting regressor to treat the neighborhood feature as categorical, so its values are handled as distinct groups rather than ordered numbers. We also set a fixed random state for reproducibility and limit training to 80 iterations. The model is then fit on the training features and target prices, learning how the inputs relate to price while properly using the categorical neighborhood information. We use a column transformer to apply ordinal encoding to the neighborhood feature, turning its categories into integer codes while leaving the other data unchanged. This lets us test how treating categories as ordered numbers influences model performance. We build a modeling pipeline that transforms the data and trains a histogram gradient boosting regressor. The neighborhood feature is encoded as ordinal values, meaning the categories are treated as ordered rather than simply distinct. The regressor uses a fixed random state for reproducibility and a limited number of training iterations. After fitting the pipeline to the training data, we can compare this ordered encoding approach with native categorical handling. We compare two models by measuring their mean absolute error on the test set. One model uses categorical features in their native form, while the other treats them as ordered numeric codes. By comparing the average prediction errors, we can see how these two ways of handling categorical data affect predictive accuracy. The output first reports the Scikit-Learn version to support reproducibility. It then compares mean absolute error for two models, one that handles neighborhood as a native categorical feature, and one that uses arbitrary numeric codes for categories. This shows how treating categories as ordered numbers can affect prediction quality and reinforces the need to handle categorical data properly. This script shows how native categorical features can improve histogram gradient boosting for housing price prediction. It uses a synthetic dataset with numeric housing details and a neighborhood category that affects price, then compares a model that treats neighborhood as categorical with one that encodes neighborhoods as arbitrary ordered numbers. The models are evaluated using mean absolute error, and the native categorical approach usually performs better because it preserves the true category distinctions. The script also reports the Scikit-Learn version and the error for each model. Monotonic constraints. Monotonic constraints help a histogram gradient boosting model keep predictions moving in an expected direction as a feature increases, while other factors stay the same. For example, higher debt to income should not reduce predicted default risk, and a larger property should not lower predicted value. These constraints reduce noise-driven, illogical predictions while preserving much of the model's flexibility. In histogram gradient boosting, monotonic constraints guide the model to follow known directional trends. A positive constraint keeps predictions from decreasing as a feature rises, while a negative constraint keeps them from increasing. Features without a reliable trend should stay unconstrained, so the model can learn their effects freely. Use these constraints only when business logic or scientific knowledge supports a clear direction. Monotonic constraints make models more trustworthy by ensuring predictions follow expected real-world relationships, which is especially important in areas like lending and medical triage. They can prevent illogical results, such as lowering predicted risk when a harmful measurement increases. But constraints must be chosen carefully, because incorrect assumptions can hide real patterns and reduce performance. With good data analysis and expert input, they help balance model flexibility with human reasoning. Python code, monotonic constraints. This section shows how monotonic constraints work in histogram boosting by comparing constrained and unconstrained models. The key idea is that a constrained model should make predictions that follow the chosen increasing or decreasing direction, while an unconstrained model may not. We import key Python libraries for the workflow: NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn for machine learning tools. The main model used is Scikit-Learn's HistGradientBoosting regressor, which fits regression data and supports exploring monotonic constraints. A small, noisy regression dataset is created to model a simple relationship between income and price. A fixed random seed makes the results reproducible. Then, 500 income values are sampled between 20 and 120. Price is generated as 50 plus 2 times income, with normally distributed noise added to reflect real-world variability. A deliberate anomaly is added to the training data by finding income values between 70 and 85 and lowering their matching prices by 70. This creates a misleading dip that tests whether the model can still learn a monotonic relationship. The income data is then reshaped into a single-column, two-dimensional format for training. The code first verifies that the input data has the expected shape: 500 rows and 1 feature. This check ensures the data matches what the model requires before training begins. If the shape is incorrect, it raises an error, so the problem can be caught early. We train 2 histogram gradient boosting regression models to predict price from income. The first model has no constraints, while the second uses a monotonic constraint, so predicted prices cannot decrease as income increases. Both models use the same random state and iteration limit, making their results directly comparable. We generate a range of income values from 20 to 120 and format them for prediction. Both the unconstrained and constrained models then predict outcomes across this same range. Comparing these predictions shows how the models respond as income increases, especially how the monotonic constraint shapes the constrained model's behavior. To compare monotonicity, we count how often each model's predictions move downward from one point to the next. Negative changes indicate violations of the monotonic constraint, so we total these drops for both the unconstrained and constrained models. The output also reports the Scikit-Learn version, then shows the downward step counts for each model, making it easy to see which one better follows the constraint. This visualization compares training data with predictions from 2 models. It plots income against price, then overlays the unconstrained model and the monotonic constrained model across the income range. The title and axis labels clarify that the key point is how the monotonic constraint prevents predictions from stepping downward. A legend distinguishes the data and model lines, so the effect of the constraint can be compared visually. This script shows how monotonic constraints affect histogram boosting regression. It creates noisy data where price should generally rise with income, then compares an unconstrained model with one forced to make predictions that increase as income increases. The unconstrained model can produce downward prediction steps around the noisy dip, while the constrained model keeps a steady upward trend. The script counts these downward steps and plots both models to show how the constraint improves consistency. In this lecture, you learn to fit gradient boosting classifiers and regressors for supervised tasks, tune learning rate, estimator count, subsampling, and early stopping, and use histogram gradient boosting features such as native categories, missingness, and monotonic constraints. In the next lecture, Lecture B, we will go over meta-ensembles.
Thank you for your attention. See you all in the next lecture.